In section 12.5, we're going to look at something called the physical pendulum. Here we're going to analyze a pendulum where the mass of the bob is not small compared to the length. And that means that we will need to adjust our pendulum equations for a physical pendulum and use these to solve some oscillation problems. Now, a physical pendulum, also called a compound pendulum, is a hanging object that oscillates about a fixed axis, but it does not pass through the center of mass. And again, this is not something that you can model as a point particle at the end of a string, but in fact the mass of this entire object is significant and therefore is not going to be modeled as a point particle, under a net force, but instead we're going to model this physical pendulum as a rigid object that is under a net torque instead. Now the object would be pivoted about the origin O, and that would be some distance h, or sometimes we'll call this a d, from the center of mass. Our center of mass would maybe be somewhere down here. Now we're pivoting it from that center of mass, again creating this torque, because gravity is of course going to act on the center of mass. We can see that force here, where the component that's actually perpendicular to the lever arm would be this piece here, or an mg sine of theta, and that would actually be perpendicular to our lever arm H or D, which means that this is the piece that actually creates some sort of a torque. And again, that is a restoring torque here that's going to always try to bring it back to the equilibrium position. Now, what that means is that torque could be set equal to this mg sine of theta multiplied by the lever arm D. And since torque is equal to I alpha, that mgd sine of theta could be set equal to I times the second derivative of theta. Just another way to rewrite alpha. Again, the negative shows the restoring nature of this force, and we can use the small angle approximation. So we can put the mgd over an I and simply rewrite the sine theta as just a theta when we use the small angle approximation, and we end up again with an equation that looks like our simple harmonic motion. So we can fit this to our simple harmonic motion equation for theta equaling theta max times the cosine of omega t plus phi. Now omega here would be equal to the square root of mgd over I. And the period, capital T, of course, is still 2 pi over omega. So in the case of a physical pendulum, that would become 2 pi times the square root of I over mgd. And again, theta max would be your maximum angular position, the furthest theta that you sort of pulled this thing out to before you allowed it to oscillate. We would want that to stick with small angles in order to have our small angle approximation actually apply. So let's try a problem together. Here we have a circular sign of some mass m that we want to hang up. This sign is maybe going to be hung from a small nail from a little loop that is at the edge of the sign. Again, it has some mass m and will have some radius r. And as we hang this thing up, it begins to just kind of oscillate a little bit. So it sort of swings back and forth once we hang it on the nail from the edge of the sign. Now our goal, again, is to here find the period of oscillation if the amplitude of the motion is small. Now them telling us that the amplitude of the motion is small is basically saying that you can, in fact, apply the small angle approximation, and our equations from the last slide will all apply. Now remember that equation that I gave you for period on the last slide for a physical pendulum was 2 pi times the square root of I over mgd. Now we need to find those values so that we can plug them in. Let's start with finding I. When you find I for this sign, we said that this was just kind of a disc shape. Now we know that the moment of inertia of a disc, or we could look it up on page 300, is a 1/2 mr squared. But that moment of inertia for a disk is the moment of inertia through the center of mass of the object. This object is not rotating through its center of mass. This is not the pivot point. Instead, the pivot point is up here. So we will actually have to apply our parallel axis theorem, which says that you could find the new moment of inertia by taking the moment of inertia through the center, or 1/2 mr squared, and then adding on an md squared, where that distance is the radius of the sign, meaning that the I value for this sign rotating through a point on its edge would actually be equal to 3/2 mr squared. So that can go in for I. For the m coming down here, again, it's still just the mass of the sign. G would, of course, just be gravity on Earth. And D, again, is the distance from center of mass to the pivot point. So again, that is also an R distance. Go ahead, take a second and simplify this, and you will find that for this sign, the period is equal to 2 pi times the square root of 3r over 2g.